On to section 5.5 and our one technique of integration from Calculus 1. So the title of this section is Indefinite Integrals in the Substitution Method. So what we'll do is introduce a technique of integration, commonly called U-substitution. And this is the only technique of integration we'll have in Calculus 1. In Calculus 2, you'll have a bunch of different techniques of integration. The title of chapter 8 in the book is Techniques of Integration, so there's lots more to follow. This is a very useful technique and not that complicated a technique, and it's really based on the chain rule and dealing with the chain rule backwards. As motivation, let's look at chain rules. Suppose we had a particular composition of functions. Suppose we have the function f of x, we represent it as u. If n is a real number other than -1, and we differentiated u to the n plus 1 over n plus 1, that is, we differentiated f of x to the n plus 1 power divided by n plus 1, we'd bring that exponent down, the n plus 1, it would cancel the n plus 1 in the denominator, we'd be left with f of x to the 1 less to the n power, and in a chain rule we'd put an f prime of x on the side, got the little arrow to indicate that the chain rule inserts the f prime on the left. Well, all indefinite integrals are sets of antiderivatives, so we're ultimately differentiating backwards. So whenever we have a differentiation formula, which we have here, concentrate on the second two, I can write it backwards and get an anti-differentiation formula, or, respecting the notation, an indefinite integral. So the derivative of the stuff in square brackets is this. So the indefinite integral of this, the indefinite integral of f of x to the n, f prime of x, must be the stuff in the square brackets plus an arbitrary constant. So if we integrate an integral of the form f of x to the n, f prime of x, that indefinite integral is f of x to the n plus 1 over n plus 1 plus a constant c, provided n's not -1, we'd have division by 0 in that case. If we were to write this in terms of the u's, notice we've got u equals f of x from up here, u equals f of x. So if we calculated the differential du, we get f prime of x dx. I think this is the first time we've seen differentials since they were originally introduced, but predictably it'd come up in this particular setting of u substitution. Well, then we could rewrite, substituting for the differential, we could rewrite f of x to the n f prime of x with u equals f of x. This would become u to the n, and this part here would be the differential du. So the integral becomes simply integral of u to the n du. It's called u substitution because commonly you let u represent some particular function. We're not stuck on the u's, but we'll use them more often than not, but not exclusively. Then it becomes an integral of u to the n du dx, and what we get from that is the same thing we had above, right? The du dx would be f prime of x. So here's du dx. We still got the differential dx there. Substituting on the right-hand side, u equals f of x gives us u to the n plus 1 over n plus 1 plus the arbitrary constant. Now, these two things are equal because the integral of this integrand, u to the n, would be u to the n plus 1 over n plus 1 plus c. These two integrals are the same. They're not the same because the dx's cancel. That's not division. Du dx doesn't really represent a quotient. It represents a derivative, which is not a quotient. It's a limit of a quotient. And what's making this tick is really the chain rule. You might remember this by thinking of the dx's as canceling. The dx's don't cancel. It's the chain rule. And we've seen this before in a certain notation for the chain rule. And I warned you then, the dx's don't cancel. It's just a notation for the chain rule. Now, it's a memorable notation that these two things be equal because it's so suggestive that we would cancel the dx's, but you can't. That's not what it says. But that's kind of the reason this d this, d that notation, the Leibniz notation for derivatives, is superior to the prime notation of Newton. In this integration setting, we'll almost predominantly use the du dx, the differential, the Leibniz notation for derivatives, though we'll probably end up ultimately really mixing it up with the Newtonian notation with the primes. So there'll be a bit of a mixture. But anyhow, largely we'll express things in terms of differentials and Leibniz notation. Let's evaluate an indefinite integral where this technique applies. Okay, so evaluate this integral. All right. The plan is to apply the chain rule backwards, to apply this U substitution stuff. I need to make this integral in a particular form. If we let f of y be 7 minus 3y squared, okay, that's a thing under the square root, then f prime of y would be negative 6y. Derivative, not differentials. We'll do it that way here in a second. Is this of the form f of y to a power times f prime of y? Well, it's close. We've got 3y, not negative 6y, but we can fix that. And notice you've got the function f of y raised to the 1/2 power because it's under a radical, a square root radical. So what we can do is take the given question. Let's tell you what, let's take this 3 and make it be a negative 6. If I'll change what's inside the integral to a negative 6, I'll need to divide by negative 2, then the quotient is 3, and so these actually are equal. So let's play that little trick. You can't argue with the accuracy of it, and I can even support the motivation of it a little bit. Hey, that is f prime of y, so that's the reason I want to see that there. We'll have a slightly more straightforward notation to deal with this, but what I'm doing is forcing it to fit the form of what we just discussed. So I can get you a negative 6y there. I got to do some arithmetic manipulations to keep the books balanced. Here's the f of y function raised to the 1/2 power. So what we've got is negative 1/2 f of y to the 1/2. That's this part here. This part here, the negative 6y, that's the f prime of y. So we get f of y to the 1/2 f prime of y, integral with respect to y. That's what we were talking about a second ago. When you get a function to a power times its derivative, we can add 1 to the exponent, divide by that exponent, add 1 to 1/2, get 3/2, divide by 3/2, multiply by 2/3. Then that's what we get for an antiderivative of the integrand. Don't forget the plus c because it's an indefinite integral. Simplify a little bit, and there you go. So there's the indefinite integral for this function. We couldn't have done this before we had encountered this, this chain rule backwards idea, this U substitution stuff. And speaking of U substitution, let's do it a different way using U's. But let me make it larger. But what we have then is the indefinite integral. We could check it by differentiating, make sure the derivative of this part of it actually is the integrand, and it is. That was a bit of a convoluted way to force it to look in a particular form. Let's try something a little bit different. And also I said you couldn't do this without U substitution. Yeah, what can you do? Well, that stuff in table 4.2 that we had encountered previously. It was the list of antiderivatives at the end of chapter 4. If it ain't in that list, and we haven't added to that list just yet, then you can't deal with it. Maybe we've added minimally to that list, but we haven't added anything like this. We could now. now that we know how to deal with this. But we'll stick with these instead of just giving a gigantic table of a bunch of integrals. And there are such things out there. In the old days, they published entire books that were just tables of integrals. But we'll approach it with the techniques of integration, and all we've got to do in Calculus 1 is worry about use substitution. Your plate will become much more full of techniques in Calculus 2. But let's try this one again, and let's do it with a slightly different notation. Here, I forced it to be a function raised to a power times a derivative of that function. Let's do that too, but let's do it using more explicitly the u's in u substitution. So let's let u equal 7 minus 3y squared and calculate the differential du. That'd be the derivative of this times dy. Derivative of this is negative 6y dy when I throw the differential in. Okay, so it's quite similar to what we just did. Do you see a negative 6y dy in the original integral? No, I see a 3y dy. All right, let's, I do have to force it to fit that. Let's multiply both sides by negative a half. That'll give me the 3y dy here. That part will be the 3y dy in the original integral. So that will be the negative 1/2 du part. Multiply both sides by negative 1/2. That'll get you 3 here. It changes the other side. There's a negative 1/2. That sounds familiar. So we had that in the other technique as well. Then we can rewrite the given integral as 3y. Let's see, that's negative 1/2 du. So there's the negative 1/2 du, should say 3y dy, is the negative 1/2 du part. So that takes care of the dy and the 3y part. We're left with a square root part. Square root of what? Square root of u. So we substituted in there, and this becomes indefinite integral of the square root of u times negative a half du. Let's get the negative a half out. And then you're simply integrating a power of the variable. And you know how to do that for all real numbers. Even -1, though that'll involve some logarithms. We'll illustrate that here in a while. So we'll add 1 to the exponent, getting 3/2. We'll divide by 3/2 as before, which is equivalent to multiplying by 2/3. Let's start skipping that step of arithmetic. Then indeed, when you differentiate, the 3/2 comes down, cancels with this, subtract 1 from the exponent. So we're on the right track. So we found an antiderivative of this with respect to u. All right, but you were asked a question that involved y's. So turn it back into an answer that involves y's. Let's see, and cancel those 2's. This becomes a negative 1/3 coefficient, and we've got u to the 3/2, but u is 7 minus 3y squared. So we've got 7 minus 3y squared to the 3/2 plus an arbitrary constant. Comfortingly, the same thing we got when we did it the other way. So if I try to match up what we stated in the notes, I'll have to put it in this form. This looks a lot cleaner, and we'll largely work them in this way, where I let u be a function of the independent variable x or y or whatever. And then we'll calculate differentials and then change all of the, in this case, all of the y's into u's. All y's must go, and it must be written entirely in terms of u's. If you're going to change the variables, you got to change all the variables. I can't mix u's and y's together, in other words. More of the same. The next result really is quite similar to what we just did. What we just did wasn't really used so much the full power of the chain rule as we used the power rule, it was called, a special case of the chain rule called the power rule, where we had powers of that function f of x or f of y. The substitution rule deals with a composition of functions, and it's really just the chain rule backwards in all its glory. Suppose u is a function of x, u equals g of x, differentiable function whose range is an interval, capital I, and suppose function f is continuous on capital I. The claim is the integral of the composition of f and g times g prime of x dx equals the integral of f of u du. All right, so what this is doing is justifying taking integrals of a particular form, and a surprising number of integrals come in this form. Taking an integral of this form, in particular, the integrand, so I want to just highlight part of it, the integrand is of this form, and changing it into something a touch more fundamental, integral of f of u du. So it's a change of variables. That's what the substitution is. You're substituting for the x's some u's, some function of u. Use some function of x. You're changing the x's into u's in some sense. Notice the substitution rule, as many techniques of integration will satisfy, it doesn't evaluate any integrals. It just changes them into different integrals. This one on the right, it looks a little bit easier than this one on the left. These techniques of integrals you'll encounter in calculus 2 are largely of that sort. They don't actually evaluate integrals. They just change integrals you don't know how to do into simpler integrals that you may know how to do. Fingers crossed. And integration is hard, and it's possible to make up integrals which exist, but you cannot find them. So there are things that are unintegrable, anti-differentiatable, if you like, in a sense. So useful stuff. There's a large body of knowledge out there on it. Let's go through a proof of this. It's just barely over a slide long. I have memories. No, it's just a slide long. It's a chain rule backwards. So the claim is the integral of f of g of x, g prime of x can be written as this type of integral. Okay. First off, suppose capital F of g of x is such that capital F is an antiderivative of lowercase f. So we could differentiate this composition, differentiate f of g of x to differentiate the outer function. It's the capital F function. Rewrite the inner function. Chain rule says add the derivative of the inner function. So there's a little arrow, totally chain rule computation. Hey, what is capital F prime? Well, I said let capital F be an antiderivative of lowercase f. That means when you differentiate capital F, you get lowercase f. So capital F prime is lowercase f. So we get, the derivative of the composition is this thing here. Well, that's exactly what the integrand is on the left-hand side. So if we'll let u, or u of x, if you like, be g of x, so there's a substitution, u equals g of x, then we can rewrite this integral as the derivative of capital F times g of x, and the substitution, the integrand on the left equals this stuff here. Okay, so there we go with that stuff there. How do you evaluate indefinite integrals? You find an antiderivative, any antiderivative, and add an arbitrary constant. Theorem 4.8 says. Can you find an antiderivative of the derivative of capital F of g of x? Certainly. Capital F of g of x. So this is saying differentiate and then anti-differentiate. Give me an answer to that. Well, here's one. Possibly there's others. In fact, there's infinitely many others, but they all differ by a constant. We've been through this in the past. So what we get for an indefinite integral of this is simply this thing here. It's differentiated and then anti-differentiated, if you like, to give the original function back. Well, somewhere in that routine, we pick up an arbitrary constant. It is an indefinite integral after all. Now, we let u equal g of x, so we could substitute in there and get f, capital F of u, plus constant c. That can be rewritten then as an integral of f prime of u du. How would you evaluate this? Using an antiderivative. Give me an antiderivative of capital F prime. Capital F itself is an antiderivative of that, because when you differentiate capital F, you get capital F prime. Theorem 4.8 again for the record. So a couple of times we've used antiderivatives to evaluate indefinite integrals. And that was the definition of an indefinite integral. Definite integrals were evaluated in a similar way by the fundamental theorem of calculus. Hey, and capital F prime, remember capital F prime we chose capital F to be an antiderivative of F. So capital F prime is F itself. So I can replace that capital F prime with F itself. That's what capital F was. And that's what we claim. That's the right-hand side of the equation. So what made it all work? The chain rule effectively made all of this stuff work. So the substitution rule, or this U substitution, this is the chain rule backwards. The textbook describes substitution, U substitution as follows. Applied to an integral of f of g of x times g prime of x, let u equal g of x, compute the differential, g prime of x dx, and rewrite the integral in terms of u's. Theorem 5.6 that justifies U substitution. For integrals of this form, the integrand has to be of quite a special form, but again, a lot of them surprisingly are of this form. They all will be that we deal with here because that's the only thing we know how to deal with beyond the stuff in table 4.2. So rewrite it as an integral of f of u du, and then evaluate the integral with respect to x and replace u with g of x. Yeah, sure, but integration involves antiderivatives, and our knowledge is, and to some degree will remain limited on what we can do in terms of simply finding these antiderivatives to do the integration. So sure, straightforward technique. I mean, that's the thing I worry about because that's the tricky thing. The rest of it's derivatives and substitutions. Okay. I made a comment earlier. Yeah, all the x's have to become u's, not just some of them, when you make the substitution to convert things into u's. Okay, I got to get rid of all of the x's. They either got to go in the g of x part or the g prime of x part. You got x's left over beyond that, you got a problem. Then you can't do it with U substitution. And we could run across plenty of integrals you can't do with U substitution. That's why there's all those techniques in calculus too. Okay, let's go through just a bunch of examples on this stuff. These are nice mechanical, straightforward things, but I'll try to inspire a technique that gives you strategy. All right, evaluate this integral. Apparently with U substitution, always start with U substitution when you have an integral, because if it works, it's easy. If it doesn't work, then you got to use some of the other techniques. This is a hypothetical conversation for calculus 2, really. So the plan is we're going to have all of this stuff become either gx or g prime of x or a function of g of x. So all the x's have to go into either g of x or g prime of x. All right. We want to let u be some function of x where we see a multiple of u prime as part of the integrand. How about this? Let's let u be 1 plus the square root of x. That's 1 plus x to the 1/2. Then when you calculate the differential, du would be 0 plus 1/2 x to the negative 1/2, 1/2 x to the negative 1/2, times dx, because we're computing a differential. X to the negative 1/2, how about I put that in the denominator as a 1 over a square root? And that works out ideally, because there's the square root of x in the denominator, like we need. There's the dx, the 2's in the way. We get it out of the way, though. And this stuff here will be the g of x. So everything here, all the x's, either go into the g of x function, the u function, or the derivative of it, the du part. It either goes in the u part or the du part when I treat it in terms of differentials. So we can do that. I don't see the 2 up here in the denominator. Oh, fine. Cross multiply and we'll get 2 du, and there's exactly what we have sitting right there. So we're going to use 2 du and u itself to change this from an integral in terms of x into an integral in terms of u. Strictly speaking, we're using theorem 5 point whatever it was, the substitution theorem that justifies U substitution, but it's just a change of variables. So let's take the given question. Let me rewrite it so it look a little bit more like what we're dealing with here. Let's take the square root of x in the denominator and write it as 1 over square root of x and split things up a little bit. Then there's u to the 1/3, and there is 2 du. So here we're substituting. It's right here. We're using the substitutions described above. 1 plus square root of x is u. So this will be that u to the 1/3 power. And this was 2 times du. So we pick up a 2 du. Let's bring the 2 out front. Now we just got to power the variable. We're all pretty limited in what we can integrate, but we can all integrate powers of the variable. Add 1 to the exponent, that'll give you 4/3. Divide by 4/3, that is multiply by 3/4. And we've performed the anti-differentiation plus c, so we've respected the notation given that this is an indefinite integral. So you need the plus c's on all the indefinite integrals. Okay, but that's in terms of u. You were asking a question in terms of x, so give an answer in terms of x. That is, change the u's back into x's. There's just one u, and you know how it relates to x. It's right here. U equals 1 plus the square root of x. Make that substitution. 2 times 3/4 is 3/2. Simplify that a little bit, and there you go. There's the indefinite integral on that one. The big strategy is I'm going to let u be some function of x, and ideally I want to see u prime sitting there somewhere in the rest of the integrand. I can get away with a constant multiple of u prime because I can move constants in and out of the integral, and I can cross multiply and move constants around between these differentials as we did. Let's do another one. All right, it's all secants and tangents. Well, that's cool because secants and tangents have traveled together throughout the derivative and anti-differentiation worlds. If I had secants and sines, I'd be most distressed. But having secants and tangents together, I'm cool with that because remember, derivative of secant is secant tangent, derivative of tangent secant squared. These things, they travel together. That's my verbiage, by the way. But I'm happy to see secants and tangents together. If it wasn't, I'd have to modify things. All right, same strategy. We want u to be some function of z this time, where we see a multiple of u prime as part of the integrand. Let's choose u to be secant of z. Then the derivative of secant is secant tangent, and there's a secant tangent right there. Also, remember, we're dealing with a chain rule, which means we're dealing with compositions of functions here. I'm not making any promises on this part, but I suspect what you're going to let u equal will be something that's inside another function. In the previous example, u was inside a square root function. In this case, u is it's both inside a square root function and a reciprocal function, right? It's in the denominator. So remember, it's based on the chain rule. So I expect compositions, and I expect u to be inside another function. And it could just be sitting there. I don't know. That's possible as well. It's inside an identity function. But a wink, wink hint is I expect the u to be involved in some other function because this is based on the chain rule and compositions. But you've got to have whatever you choose for u to be, you've got to have the derivative or a multiple of it sitting around somewhere. So you got no choice but to let u equal secant z. Then the differential, derivative of secant is secant tangent. So we get secant z tangent z dz for the differential. And there's secant z tangent z dz right there. So we can take this, maybe write this as 1 over secant z to the 1/2 and get the secant z tangent z dz stuff over on the right-hand side. So all I did was split things up and change the square root into a 1/2. We're going to get power of that pretty soon. We could write that then as secant z to the negative 1/2, if you like. Making the substitution, u equals secant z. That'll give us a u to the negative 1/2. And all that stuff there is du. We didn't have to deal with any multiples of 2 or anything like that this time. So that simply is du. So we've substituted. Right there is where we're using that substitution theorem. And it reduces down to an integral of u to the negative 1/2 du. Piece of cake to integrate. Add 1 to the exponent. Add 1, negative 1/2 plus 1 gives us positive 1/2. Divide by 1/2, same as multiplying by 2. So the anti-differentiation is right here. One more time. You don't know how to anti-differentiate very much stuff, but you know how to deal with powers of the variables. I don't know how to anti-differentiate very much stuff either, but I know how to do powers of the variable. So add 1, divide by what you get. Don't forget the plus c. Here we've done the anti-differentiation and respected the indefinite integral notation. And that we could write in terms of square roots, if you like. And u was secant z, so we'll make that substitution. And there you go. So there's the indefinite integral of the given integram. How would you check it? I'd differentiate this and see that we get the integrand back, and you will. Hey, when you differentiate this, what rules are you going to have to use? Chain rule, because that secant function is stuck inside a square root function, right? We'd have something of the form 2 secant z to the 1/2 power. We bring the 1/2 down front, it'd cancel with this 2. We'd subtract 1/2, that'd give us a 1 over square root of. And then we'd multiply by the derivative of the stuff inside. Derivative of secant is secant tangent. There's that square root I was talking about with a negative 1/2, and it's in the denominator. It checks. Let's do another one. Same strategy. U is some function of the variable, and du, I see that sitting around elsewhere in the integrand. Let's try this one. All right, any ideas what you're going to let u equal? What's the derivative of the log function? 1 over function. Okay, so this one's going to need a little manipulation before we can use u substitution. First, log square root of t, log t to the 1/2. I can bring that 1/2 out front. There you go. And then we get log t over t. Well, now we're in business. If we let u be the log function, then the derivative of log t is 1 over t. And there's a 1 over t. So that's going to work out appropriately. If I let u equal the log of the square root of t, it ain't going to work out, because the derivative is 1 over the square root of t times the derivative of the square root of t. Yeah, I don't think that's going to work out quite so smoothly. This will. So let's simplify it first. It requires some manipulations, unless the algebra in my head's a little mixed up, which is quite possible, but this certainly works. And this is more straightforward. I see a function and its derivative right there. So we'll let u be the log function, then du is 1 over t dt, the differentials. We could take the given integral, algebraically rewrite it like this, maybe split up that quotient as a log of t times 1 over t dt. Then the 1 over t dt stuff, that's the du part. Log t is the u part. So right here, using the substitution theorem, changing all the t's into u's, either u's or du's. Everything's accounted for. We didn't have any constants to deal with beyond the 1/2 that we took care of earlier. Integrate u, 1/2 u squared plus a constant. Simplify, it's 1/4 u log t squared plus a constant. Substituting back in to put it in terms of t. So the u's were just used in passing to give us something that's elementary, get something that's so elementary, even we can integrate it. In calculus 2, you're still going to be stuck with only actually evaluating integrals of fairly elementary things. And that's what the world is stuck with. Whenever the integral sign disappears, don't forget the plus c's on indefinite integrals. But that must have been the integration of, I'm going to predict here, a fairly elementary function, because that's really all anybody knows how to anti-differentiate is fairly elementary functions. People know how, here's how I know more stuff about integration than you do. I know how to take more complicated functions and change them into elementary functions than you know, but you'll catch up with me in calculus 2. In the end, the integration, the anti-differentiation is ultimately it's performed on a fairly elementary function. That's all anybody knows. Let's do another one. Okay, this one, I'm trying to find them that are progressively more complicated. We want to let u be a function of e to the theta, where we see a multiple of the derivative, say u prime, as part of the integrand. You're going to let u, first guess, how about we let u be e to the 2 theta minus 1? That satisfies some of the stuff I described in the past. That puts u in a composition. We'd have 1 over the square root of u. Yeah, but then du is going to require you find a 2 e to the 2 theta. And there aren't any more 2 thetas. I'm sorry, there aren't any more e to the 2 thetas. So that's a little bit of a problem. So on this one, it's trickier. All I know how to integrate is stuff in table 4.2 from section 4.8 on antiderivatives. So does this look like any of those? Well, the closest one I can find that matches it is this one. Table 4.8, number 12, actually table 4.2.a. I've set constants equal to 1 in that one. It's a simplified version of table 4.2. The entry number 12 in the simplified version is exactly this. This is the only one that has a 1 over square root of stuff squared minus 1. So if any of them look like this, it's this one. And it was related to secant inverse. All right. Well, let's try to make it match this. I'm still worried. There's no x out there, but I can't think of anything else to do. So I tell you what, let's let u equal e to the theta. Then this will be u squared minus 1 because of the 2 on it. And this is e to the theta squared, e to the 2 theta. So this is u squared minus 1. We'll get this part under the square root, but we got, I don't know, it seems like we're missing this part. Also, du is going to introduce some other stuff. Well, it turns out those balance off. So if we calculate du, we'll get du equals e to the theta, d theta, differentiate the exponential, nothing happens. Put the d theta on there because you're computing a differential. Well, I could do this. We could divide both sides by e to the theta to get du over e to the theta equals d theta. I want to do everything in terms of u, but u equals e to the theta itself. So I could take that denominator and write it as a u, because e to the theta is what u is. So we actually get the relationship du over u equals d theta. Okay, I recommend you practice these. This one doesn't fit the mold as easily as the others do. That's one reason I wanted to work it. So this one's a little bit trickier. I couldn't think of anything else to do. It's a question out of the book, so I'm supposed to know how to do it. Let's try this. Turns out I think this is going to work. All right. But I've got a lot of practice with these. So it hasn't worked if I can't take all of these thetas and turn them into u's. But I think I can, because we could rewrite this as e to the theta squared, right? It's an algebraic manipulation. Now, like we said, u is e to the theta, so I can get rid of that. D theta, can you convert the d theta into u's? We can. In fact, d theta is du over u. So we'll make that substitution. So right here is where we're changing variables with that equal sign. We get 1 over square root of u squared minus 1 times du over u. Hey, that's spot on. If we'll take the u, let's put it in the front of the radical. So we get an integral of 1 over u times u squared minus 1 square root of du. Yeah, that's exactly this with u's instead of x's. And we know this gives us a secant inverse. So this gives us a secant inverse of u plus a constant. U was e to the theta. Substitute that in, and there you go. So there's the indefinite integral. I agree that one was trickier than the previous ones. We did this oddball manipulation in the short term of having u's and thetas on the same side of the equation. That injustice will not stand. So we got to do something with it and have u's on one side of the equation and thetas on the other, so that when we change from thetas to u's, all the thetas are gone, all the e to the thetas are gone, everything has become u's and du's. And it worked. Yeah, it worked because it's a textbook example. But this one, granted, is trickier than the others. Okay, this is an example out of the book. Ask you to evaluate the integral of tangent. Okay, this one's actually less tricky than the previous one. Integral of tangent. How about we write tangent as sine over cosine? I can do that. I like seeing sines and cosines together. Tangent all by itself, I don't know what the integral of that is. We hadn't done it yet. Apparently, since it's popping up now, it requires u substitution. Okay, well, let's write tangent as sine over cosine. Can you use u substitution on that? I want to let u equal something where I see its derivative also as part of the integrand. Any ideas? Hey, the derivative of sine is cosine and the derivative of cosine is negative sine. Maybe I could let u be either of these. Let's try, it says here u equals cosine. Let's try that and make sure it works. If we let u equal cosine x, then du, derivative of cosine, is negative sine of x dx. Is that going to work? I can get the negative out of the way as we do in the next line. You see a sine x dx there? Yeah, there's a sine x dx, and there's the u thing. So here's the du part, and there's the u part. Suppose we let u equal sine, because the derivative of sine is cosine. I won't have to deal with the negative sign if I do that. If you let u equal sine x, then du is cosine x dx. Do you see a cosine x dx here? Not exactly. I see a 1 over cosine x dx. I don't see a cosine x times dx, if that's the way you want to read that. I see it in the denominator. I see a cosine, but it's not in the right place. So if you try to let u equal sine x, it won't work. You have to do it this way. But this way works ideally, though it would be tempting to do it either of those two ways, but write it out. You see it won't work when I let u equal sine. This one works just fine, so that we can rewrite sine x over cosine x dx as 1 over cosine x, sine x dx. With this substitution, u equals cosine. This becomes a 1 over u. Sine x dx, we went through the computation. That gives you a negative du, and you're simply integrating, bring the negative out front, you're integrating 1 over u du. Integral of 1 over u, natural log of the absolute value of u. Remember the absolute value that we picked up when dealing with indefinite integrals of natural log functions, or antiderivatives for that matter. See table 4.2. There was an example we dealt with in the past that says you need absolute values on this for a general result. So we get negative natural log absolute value of u plus c. The integration was done right here. Yeah, I don't know how to integrate much, but I know how to integrate 1 over u. It's a natural log of the absolute value of u. I know how to integrate powers of the variable, and it became that. It's a special one that introduces a log function, but we've seen that from the past. Converted back to x's. U was cosine x, so I put a cosine x in there. And there's the indefinite integral. All right, the book may actually express this as the answer. You know what, I want to change its form a little bit. I can't argue this. This is the indefinite integral. You know how we've seen sines and cosines together, secants and tangents together? I want to see secants and tangents down here. I want to see cosines. We started with a tangent. I expect to see my answer in terms of secants and tangents. So for that motivation, tell you what, let's take this negative sign inside the log function as an exponent, property of logarithms. What is 1 over cosine? That's secant. So I can rewrite this as the natural log of the secant of x, absolute value, plus a constant. Let's write the answer like that. If I got to sit down and memorize these things, I got a way better chance of remembering it if there's patterns. And the pattern with differentiation and anti-differentiation has been secants and tangents are together. Sines and cosines are together, and cosecants and cotangents are together. So I'm going to be a little insistent on writing the integral of tangent of x as natural log absolute value of secant of x plus a constant. not this. I mean, they're equal, so I can't argue with this, but that's easier to remember. So there's something new. We know how to integrate the tangent function now, something we couldn't do in the past. Your table 4.2 that had all those antiderivatives could now be extended to include tangents. Let's do secant. That wasn't in table 4.2. And this one's trickier still. The reason I wanted to do it, probably the reason it's a worked example in the book as well. Let's take the integral of secant x and let's multiply it by secant x plus tangent x over itself. So I'm multiplying by 1. You can't argue with the validity of that. You could argue with the motivation of it. Part of the motivation is I can't think of anything else to do. This is the standard trick to deal with this, but it is a trick. You should be able to follow all this and believe all the steps, but I can certainly believe I would have never thought to multiply by this. But you can. Let's distribute in the numerator. That secant will give us a secant squared plus secant tangent. Secant squared plus secant tangent. We got this in the denominator. And I'm looking for some u substitution. I want u to be something where I see its derivative in the integram. Let's let u equal secant x plus tangent x. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. So here's the differential. Do you see this up there? There it is, secant squared plus secant tangents, written in the opposite order, but there it is. So this u substitution works. And we can take the integral of secant, which we know to equal this, as above, maybe split it up. This would be the u part. This would be the du part. So it actually works out really cleanly. No constants to move around. We just get 1 over u du. Applying that theorem, you know how to integrate 1 over u. It's natural log of the absolute value of u. Write it in terms of x's. U equals secant x plus tangent x. There's the indefinite integral. It worked. And it's got secants and tangents together. So I ain't going to fiddle with this one. I like seeing secants and tangents together in integrals and derivatives. It's a pattern that helps me remember some of this stuff. So there's something else you could add to table 4.2. The integral of secant is this stuff down here. You think you could figure out how to integrate cosecant x? Odds are I'd multiply by cosecant x plus cotangent x over itself. And something similar would happen. It works. It does. Possibly that's one of the other parts of this example 5.5.8b in the book. Also, I'm going to step out on a limb here and speculate. I bet you the integral of cosecant x is negative natural log cosecant x plus cotangent x, absolute value plus a constant. I bet I change all the cofunctions and introduce a negative sign. I bet you that's what happens. Possibly I'm off a little bit, but that's the kind of patterns we've seen before, and I think that's correct. But I am a little rusty at this myself. But the computation it's a similar trick for cosecant. I think where we stand at this stage then is you actually now know how to integrate the first power of all of the trig functions. Sine and cosine, no problem. Secant and cosecant, here's secant. Cosecant's a similar way. Tangent, we did tangent previously, and cotangent would work in a similar way. So I think we could expand that table now, at least to include the first powers of all the trig functions. I think it included some of the second powers. Okay, here they're having you evaluate the given integral 3 different ways. We ought to get the same answer with all of them. Their point here is clever observations and mental calculus computations save you a bunch of algebra. I think that's their point. But we're integrating the square root of 1 plus sine squared x minus 1 in the square root times the sine of x minus 1 times the cosine of x minus 1 dx. Okay. Any ideas on what you'd let u equal to? my first attempt would let u equal this thing under the square root, because I'm thinking chain rule, and I expect the u thing to be raised to powers or inside other functions. What's the derivative of sine squared 1 plus sine squared x minus 1? Derivative of the 1 is 0. We bring the 2 down, we get the sine. Derivative of sine is cosine. That sounds pretty promising. Actually, that's the third way they want us to do it. But first, they're going to have us do this by making a u substitution, and then a v substitution, and then a w substitution. So u substitution, quote unquote, 3 times over. All right, we'll follow their lead because they told us to. First, let u equal x minus 1. If you do that, du equals dx. So that's what we get in terms of differentials. Can you take all the x's and turn them into u's? Yeah, the x minus 1's just become u's, and the dx becomes a du. So this becomes 1 plus sine squared u, square root of sine u cosine u du. All right, that was a very much a baby step in terms of changing the form of it. Secondly, they say let v equal sine u. All right, they told us to do that. Let's try that. If you do that, then we need the differentials. dv, derivative of sine u is cosine u, du for the differentials. Okay, do you see a way to change all of this stuff into v's? Yeah, the dv part would be this, the cosine u du. This is where we left off in the previous line. This would be v, and this would be v squared. Substituting in, we get 1 plus v squared times v times dv with a square root over the first couple. We get this here with a square root over the first two. This one actually looks very similar to the very first thing to which we applied u substitution. And they give us a hint to let w be 1 plus v squared. This is going to work. Yeah, the derivative of 1 plus v squared is 2v, and there sets a v. So this is going to work. Let w equal 1 plus v squared. So that dw then is 2v dv. I see a v dv, so let's divide the 2 out to get dw over 2 equals v dv. Then we can take this integral where we left off, substitute in 1 plus v squared equals w, so we'll have a square root of w for this part. V dv is dw over 2, dw over 2. So we've substituted, we use the theorem there on this third substitution. And that simply gives us, bring the 1/2 out front, a power of the variable w. W to the 1/2, add 1 to the exponent, divide. The integration has been done. Now it's a matter of unwrapping all these variables that we've introduced, taking it from w back to v. W is 1 plus v squared, so we'll substitute 1 plus v squared in there. There's your 1, so cancel the 2's, 1/3. Stuff to the 3/2. This stuff has become 1 plus v squared. Don't forget the plus c. And taking the v back to u's, v was 1 plus u squared. So we get, no, excuse me, we've got the v's, so go back to the v's. V is, looking in the wrong place. There it is. V equals sine u. I was looking at part B. Yeah, V equals sine u. There it is right there. So from V's back to U's, V equals sine u. Substitute that in. There we go. And finally, take the U's back to X's. And let me look in the right spot. U equals X minus 1. The U becomes an X minus 1. And there's what you get for the indefinite integral. All right, well, this is just U substitution done in tedious detail. Apparently, there's quicker ways, and in part B and part C, they've asked us to do it in the quicker ways. Is this correct? Yeah, if you'll differentiate this, you'll bring the 3/2 down. We'll get some cancellation there, leaving us, I think, with a 1/2. We'll rewrite this, subtract 1. That'll give us a 1/2 power on this. Okay, that's this part here. Chain rule will then have you multiply by the derivative of this, which will produce 2 times this times that, sine x minus 1, cosine x minus 1. And we had a leftover 1/2. It checks. Let's do it again, but with different substitutions. Now they tell you try these substitutions. Okay, let u equal sine x minus 1, because they said so. That'll give us du equals derivative of sine is cosine x minus 1 times 1. And I suppose I've technically used the chain rule here, but I didn't indicate it. Let's maybe gloss over those steps. I'm multiplying by 1, so it doesn't change anything, but the chain rule does apply. So they told us to use that as the first substitution. Now here, can you take everything and write it in terms of u's? Here's a u, here's a u equals sine x minus 1. And here is du, cosine x minus 1 times dx, as we had up there. So it works, and we can rewrite it as this integral one more time. Substitution, u substitution, doesn't integrate anything. It just changes the forms of integrals. Most techniques of integration are really not techniques of integration. They take integrals and they turn them into other integrals. They take integrals you don't know how to do directly and they turn them into integrals that you do know how to do directly. So that's what we're doing here. We're changing this into a new integral. You know how to integrate this? I got a pretty good idea that we're going to use substitution, and they've told you the substitution to use. So next, let v equal 1 plus u squared. Okay, so it's the stuff under the square root. The dv part will involve 2u du. There's a u du right there. We'll just have to account for the 2. Let v equal 1 plus u squared. dv, 0 plus 2u du. Let's get the 2 out of the way. Is dv over 2 equals u du to match it up exactly. Then we'll have the square root of v, and this will be dv over 2. Square root of v, dv over 2. Let's bring the over 2 out front. Let's write the square root as a 1/2 power. We're better at integrating powers. I am better at integrating powers of the variables and dealing with the radicals. Add 1 to the exponent gives us 3/2. Divide by that gives us 2/3. We get some cancellation there, giving us 1/3. V to the 3/2. V is 1 plus u squared, so 1/3, 1 plus u squared to the 3/2. Plus a constant. Last step, get rid of the u. We let u equal sine x minus 1. So make that substitution here, giving the answer in terms of x, and the same thing we got last time. So one less layer of substitution. Really the point is, if you think ahead, you might be able to avoid some of the substitutions. As long as you can perform substitutions and you can change it from one integral to the other, you must be on the right track in these textbook examples. Part C says do it again with a different substitution, a single substitution. Okay, so this time they say use the substitution u equals 1 plus sine squared x minus 1. Yeah, that's what I speculated originally because that looks so chain rule-ish. Composition of functions, u inside a square root function is what we're going to get. Of course, I worry about what happens over here. They told us to do this. Fine. Let u equal 1 plus sine squared x minus 1. Then du, derivative of 1 is 0. Sine squared, so it'd be 2 sine x minus 1 to the 1 power. Inside that squaring function was sine x minus 1, so we'll multiply by the derivative of sine x minus 1, which is cosine x minus 1. Derivative of x minus 1 is 1. I did stick the 1 in this time. There's some variety. It's a composition of 3 functions. The x minus 1 function is inside the sine function, and that's inside the squaring function. 3 layers of functions, 2 applications of the chain rule, 2 applications of the chain rule. Back when we were studying chain rules, we talk like that. So let's see, let's drop the 1 in the square brackets and move that 2 to the other side. So du over 2 is sine x minus 1, cosine x minus 1 dx. Perfect. That's exactly what's sitting on the right-hand side. So we can take the given integral and in one step, change it into terms of u's. We've got a square root of u here. This stuff is just du. Sine x minus 1 cosine x minus 1 dx, du over 2. So it becomes an integral of the square root of u, du over 2. Bring the 2 out front. Integrate u to the 1/2. I think we've done something like this before a couple times. Add 1 to the exponent, divide, simplify gives you 1/3. Substitute in the u value given here, and that's the same thing. We got the other 2 times. So there's 3 different ways to work the same problem, requiring progressively more insight. Yeah, but you're progressively luckier in terms of how much substitution you have to do. With a clever substitution, I can simplify things to a single substitution. It does take a little bit of insight and experience to recognize this. Let's see what's next. Yeah, let's go back to the notes. We mentioned something about integrating cotangents and cosecants. I mentioned that verbally. What we could add to our table of integrals is the following. Oh, good. Let's see if I guessed it correctly. I think that's what I said when we were looking at the integral of secant. We can use that same technique to go through and find integrals of cotangents and cosecants. We did these 2 in examples. And as I mentioned, now you can integrate the first power of all 6 trig functions. We already knew how to do sine and cosine. It's a little surprising we didn't know how to integrate the secant, tangent, cosecant, cotangent functions until we had u substitution. Yeah, they all required it as well. And each one led to a logarithm. All right, let's see. So next is to deal with a couple more examples involving initial value problems. So we made some comments about this in the previous section. So what we're up against here is they've given you a derivative, they've actually given you a second derivative, an initial value of the derivative and an initial value of the function. So they have given you an initial value problem. It's called a second order initial value problem because it involves a second order of differentiation. Second derivative, second order differential equation. We'll have to anti-differentiate twice. That's why they've given you 2 initial conditions. We've done these before, I think mostly when we just had a first derivative and a single initial condition. It's like 2 of those problems for the price of 1. It's one inside another. All right, so the question is, find a function y that has this as its second derivative. When you plug 0 into it, you get out -1. And when you plug 0 into its derivative, you get out 4. All right, let's use the notation involving indefinite integrals with proper respect. It's that notation. First, dy dx, the derivative of y, is an element of the indefinite integral of the second derivative. That's just an expensive way of saying the derivative itself is an antiderivative of the second derivative. Yeah, I need to anti-differentiate once, but I'm respecting the notation. Remember, we defined indefinite integrals as sets or collections or families. Sets is the cleanest way to discuss it, but I'm trying to prepare you for verbiage other people may use. Second derivative is this thing here, so we'll substitute that thing in, and we need to first evaluate the indefinite integral of 4 secant squared 2x tangent 2x. Okay. Any ideas on this one? What you might let u equal? Are you happy? I got secants and tangents together, so things could be going worse. So I want to let u equal something whose derivative is floating around there. I may have a bit of liberty on this one. Derivative of tangent is secant squared. Derivative of secant is secant tangent. So I think you can't lose whether you take u equal to tangent or u equal to secant. I've written it up here in terms of secants. You want to let u equal tangent, derivative of tangent secant squared, and there's a secant squared right there. I think that'll work too. Let's let u equal secant 2x, always of 2x, to keep the same arguments in the trig functions. Then the derivative du, the differential du, will be secant 2x tangent 2x. Derivative of secant is secant tangent. You'll pick up a 2 by the chain rule, because we had 2x inside that function, and then stick a dx on there because you're computing a differential. Divide both sides by 2. That'll give you a du over 2 equals secant 2x tangent 2x dx. And except for the 4, that's the rest of the integrand. We've got a secant here, a second secant here, and a tangent here. So everything will be accounted for. So we can take the given integral, let's bring the 4 outside, split the secant squared up into this product, and say, hey, I want to view it as that's u, and this is the du stuff. In this case, du over 2. I call it du stuff because I may have some slight manipulations performed on the du itself. We get the 4 out front. This is u. This is du over 2. Substitute exactly that in. Maybe bring the 1/2 out front, cancel with the 4 to give a 2. And all this stuff settled down to simply the integral of u. Easy enough, 1/2 u squared. Add 1 to the exponent and divide. We can cancel that. We will in the next step. Don't forget the plus c because it's an indefinite integral. We get u squared plus c. U was secant 2x. So we'll plug secant 2x in, giving us secant squared 2x plus a constant. So where are we here? We're in the indefinite integral of the second derivative. I know the derivative is an element of that set. This is a set of functions of the form secant squared 2x plus some constant. So if I pick a particular one of those, like dy dx, it's going to be of the form secant squared 2x plus some specific constant. I've represented those specific constants with lowercase k's. I'm going to use a lowercase k sub 1 this time because we're going to do this twice. So the form of dy dx, or if you like y prime, is secant squared 2x plus a constant. Let's call that constant k sub 1. I'm reserving the plus c notation to mean an arbitrary constant in a whole set of functions. All right. How are you going to find this k sub 1? Like we did before with initial value problems, using an initial condition. This is y prime. There's an initial condition for y prime. When we plug 0 into y prime, we're supposed to get 4 out. Okay. Plug 0 into y prime, supposed to get 4 out. Well, then plug 0 into y prime. Y prime of 0 would be secant squared 2 times 0 plus k sub 1. That's secant squared 0 plus k sub 1. Secant of 0 is 1. It's 1 over the cosine of 0, which is 1 over 1. It's 1. Plus k sub 1. And we want that to equal 4. So we plug 0 in. We get 1 plus k sub 1. It's supposed to be 4. Set it equal to 4. Looks like k1 will have to be 3. As always, we use the initial condition to find the constant of integration, it's called. So what is dy dx? Secant squared 2x plus 3. There it is. But we ain't looking for dy dx. We're looking for y itself. We'll do it again. So next, y is an element of the indefinite integral of dy dx. In other words, y is an antiderivative of its own derivative. Dy dx, we saw, previous slide, was secant squared 2x plus 3. So we need to deal with that. You know how to anti-differentiate secant squared? Derivative tangent secant squared, isn't it? Yeah, so this will involve a tangent. It's coming down the road. It's got a 2 inside it. If you go to table 4.2 in chapter 4, section 4.8, with k equals 2, you'll see a formula for this. I'm really not hung up on those formulas with the k's in them that they give in that table. Let's do it with u substitution. Then I don't have to remember any table stuff. I need to remember antiderivatives a little bit, but forget the k stuff. Let's let u equal 2x. Let's do a second substitution. So du is 2 dx, divide by 2, we'll get du over 2 is dx. Then we can take this integral and rewrite it as secant squared u plus 3 dx. Well, dx is du over 2. Bring the over 2 part out. We need to integrate secant squared u plus 3, piece of cake. Secant squared is a derivative of tangent, so we'll get tangent. It's the antiderivative of u. Antiderivative of 3 with respect to u is u. Plus we get the constant, the arbitrary constant, because it's an indefinite integral. What are we doing? Distribute the 1/2 to produce this alternative form. Take the u equals 2x and substitute that back in. So that produces this as this indefinite integral. So we're almost there. Y is an element of this indefinite integral. So y is of this form. That is, for some constant, let's call it k sub 2 this time, we get y is 1/2 tangent 2x, 1/2 tangent 2x plus 3x plus k sub 2 for some given constant. And to solve an initial value problem is to find all these constants. What's that constant? Well, they told you an initial condition for the function itself. Y of 0 equals -1 was given, so we'll plug 0 into this, set it equal to -1, and solve for k sub 2. Plug 0 in, we get 1/2 tangent 2 times 0 plus 3 times 0 plus k sub 2. That's simply k sub 2 on the left-hand side. The right-hand side is -1. K sub 2 must be -1. Plug that in up here, and that'll give you y. Y is 1/2 tangent 2x plus 3x minus 1, as given down here. 2 initial conditions. Yeah, because we had a second order derivative, and we had to work back to the first derivative, yielding a unknown constant of integration. We'll use that first initial condition to find it, and then go from the derivative back to the desired function itself by anti-differentiating a second time, getting an unknown constant, and dealing with a second initial condition. It's really 2 problems for the price of 1. Like I said, it's 1 problem inside another, a first derivative problem and a second derivative problem, both of which are worked in terms of antiderivatives, or if you prefer the notation, indefinite integrals. And indefinite integrals are part of the title of the section, so let's use that notation and use it correctly to get you used to that. And I guess that's all the examples, and that's also all the notes. Okay, so there's your one and only technique of integration. U substitution. Substitution method is really just U substitution. What's left to do is some slight applications to areas between curves involving U substitution, and then we'll be done with Calculus 1. Have a nice day. I'll see you in the last section in a little while. Bye-bye.